turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology. Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to the Naked Scientists podcast, the show that brings you the biggest breakthroughs in science, technology and medicine with me, Chris Smith. And today, NEOs, near-Earth objects. What are they? And are some of them on collision courses with some of our biggest cities? And if they are, what can we do about it?
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
Asteroids and comets that pass close to our planet are termed NEOs, or near-Earth objects. These entities date back in some cases to the origins of the solar system, and they have in fact shaped Earth's past, sparked scientific curiosity, and they've even provided the inspiration for some Hollywood blockbusters. But what exactly, and where exactly, are they? And do any of them have any real chance of slamming into the Earth in the near future? And if so, what can we do about it? Well, that's what we're going to explore this week, starting with Richard Binzel, who's Professor of Planetary Sciences at Massachusetts Institute of Technology.
A near-Earth object is pretty much what it says. It's an object or an asteroid, could be a comet, that happens to come passing near the Earth. When we say near the Earth, that means somewhere closer than the orbit of Mars and a bit closer than the orbit of Venus. So a near-Earth object is just something that comes to our neighborhood.
Of any size?
Yes, of any size.
Now, you mentioned two words there that are quite commonly used, asteroid, comet. They are different. What's the distinction?
Well, first off, it's the appearance that will distinguish what we call an asteroid and what we call a comet. If it looks like a tiny little star or star-like, is an asteroid. But if it's fuzzy, we call it a comet. But generally speaking, they have two different origins. Asteroids tend to come in from the asteroid belt, which is between Mars and Jupiter. And comets tend to come from way out in the far reaches of our solar system. They've been stored out in the deep freeze, if you will. And then these comets, which are now icy, they come in close to the sun, they heat up, the ices melt, and the gases that come off give them the fuzzy appearance.
And how big are these bodies, the asteroids and the comets, and how numerous are they?
The Earth sweeps up tons and tons of dust every day. So it's innumerable particles of stuff out there that are dust size. Pebble-sized things fall through the atmosphere every hour. A few times a year, there's a big enough chunk, maybe the size of a small car, that enters the atmosphere. The atmosphere shields us. It's the friction of the body moving through the atmosphere at high speed. That friction basically vaporizes the outer layers and breaks the object apart. Something big enough to give us meteorite samples falls a few times per year on the Earth. Of course, most of the Earth is water, so getting one to land in your backyard is incredibly rare, but it happens. But when we get to objects the size of our recent friend, 2024 YR4, that's about 50 meters or so. If you sat it next to Nelson's Column at Trafalgar Square, it would be just about the same height. And we think an object like that size, 50 meters, comes wandering by the Earth-Moon system many times per year. So it's not uncommon that these space rocks come wandering by.
And what pulls them onto an Earth-crossing orbit? Because obviously we've been here for over 4.5 billion years. So it's slightly surprising there's still stuff for us to run into.
That's a really interesting question because, the asteroid belt where most of these come from is between Mars and Jupiter. But Jupiter's kind of the big bully in the solar system. It's the most massive planet. And Jupiter is always tugging on those orbits of those asteroids, thousands and millions of asteroids. And occasionally it will tug on one just right so that instead of being in a mostly circular orbit, an asteroid might get nudged out of the asteroid belt, mostly by Jupiter's gravity, into a more elongated path or elliptical path. And that path, as it goes around the sun, can come closer to the sun than the Earth, and that lets it come into our neighborhood, and we would call that a near-Earth or Earth-crossing asteroid.
And what sort of damage can these things do? relative to their sizes? And how do we know that?
Things that are as small as a car and smaller burn up very effectively in the atmosphere. When they're a bit larger, like Chelyabinsk in 2013, may have been something 20 meters across or so. That's an object where the atmosphere shields us, but the object breaks apart close to the surface. And even though we don't get pummeled to make a crater, the pressure wave that that meteoroid, if you will, has been pushing through the atmosphere. That pressure wave will hit the ground and break windows. That as happened in Russia in 2013. But things large enough, maybe 100 meters or a few hundred meters across, which would make a crater if they landed, that may happen once every few thousand years somewhere on the Earth. And we'd rather not have it land over a populated area. But again, those are incredibly, incredibly rare.
And the one that did for the dinosaurs that caused the Chicxulub impact 65, 66 million years ago, how big was that?
Yes, at the top end of the scale, something about 10 kilometers across is what was the bad day for the dinosaurs 65 million years ago. In that case, the impact did make a crater off of the Yucatan Peninsula of Mexico. And the consequence of such a large impact was that dust and debris filled the atmosphere. So it wasn't just that you were in the wrong spot, but so much dust and debris was kicked out of the crater that 10-kilometer impactor made that probably the Earth went dark. The sun was blocked for months or maybe a couple of years. And if you were a plant-eating animal, you didn't survive. And if you were somebody who fed off of plant-eating animals, you didn't survive either. It turns out mammals at that time were burrowing creatures that could survive off of seeds and whatever and scavenge some good old dinosaur meat lying around. The mammals survived, and so the fact that the dinosaurs didn't have a space program is why we're here today.
I suppose in some respects that's a good thing. It gave us our break, didn't it? But do we also have these incoming bodies to thank for the fact that we actually have the environment on the Earth we have at all? Because the Earth, when it first formed, was pretty hot and pretty dry. And some people have put it to me that most of the water arrived from space on these bodies.
Well, for certain, the water and basically everything we have in our chemistry that makes all of life came from outer space, and that's the ingredients that form the planets. So it's a question of what was the last layer that came in that gave us water, gave us the organic chemistry for life. And that may have well been meteorites. It may have well been the Earth sort of cleaning up the leftover debris from the formation of the planets. We're talking 4.5 billion years ago. That could have been the ingredients that allows us to have a conversation today and sip our morning coffee.
Makes you think that, doesn't it? That was Richard Binzel. He's at MIT. Now, on the subject of how life's chemistry could have come from outer space, the nearby asteroid Bennu was recently visited by the OSIRIS-REx mission, which managed to collect and retrieve a sample from Bennu's surface, some of which landed on the desk of Sarah Russell, who's at the Natural History Museum in London, where she's been analysing it. And it's revealed some intriguing insights into how asteroids might, in fact, have cooked up all kinds of life-linked exotic molecules in deep space and then potentially delivered them to Earth.
The reason that we picked Bennu is we thought it was a stony meteorite, and these are really interesting because they formed right at the beginning of the solar system 4.5 billion years ago, and they can tell us what the environment was like when planets were first forming. And Bennu was particularly interesting because it's very dark, which implies that it might have a lot of carbon in it. So we were hoping that it would be full of organic material and water, and it turned out that it was. And that's really exciting because then it can help tell us perhaps about how the Earth became habitable, how the Earth got its water, and how carbon came to the Earth.
And how did you actually study it then? What was the mission that went there and retrieved the samples that you've now got?
Yeah, so the mission was called OSIRIS-REx. It was a NASA mission that launched in 2016, and it sent a spacecraft to go around the asteroid Bennu, which is about 500 meters across. And it spent about 2 years mapping the surface. So we've got some fantastic data about what the whole of the asteroid looks like, learn about what it was made of. one of the things that we learned was that it's actually a rubble pile. So it's not a solid body, but it's just a pile of boulders sort of just loosely stuck together under its own gravity. The climax of the mission, this arm came down to the surface of Bennu, and we were originally thinking that it would be quite a solid surface, but actually it was like a ball pit, and the arm went straight through. Luckily, it had some thrusters to kind of push it back again, and it collected about 121 grams of material, which then brought back to Earth.
Of course, there's one other way that you could get your hands on a sample of Bennu, which is if it has a slightly closer encounter with Earth than we would have liked. Is that on the cards, or is it way off on an orbit that means it's very unlikely to hit us?
No, it is a near-Earth object, and it does have a small chance of hitting the Earth. So it has a chance of 1 in 2,700 of hitting the Earth in September 2182. So we don't need to worry about it for another 150 years, but it would be quite a nasty collision if it happens.
Something we've learned about it, as you say, it's a rubble pile. So does that have implications for how we might deal with it and its ilk? So there's presumably a number of them that are like this. And if we just shot something at it, is there not moreover a chance that it'll just fall apart into lots and lots of bits, so we turn one problem into a million?
Yes. Well, yes, there is that problem. So the NASA DART mission actually tried to see if the trajectory of an asteroid could be changed by having an impact into its surface. And there's a ESA, European Space Agency follow-up mission called HERA that's on its way to see what exactly happened. But it seems like that was successful, that we can move an asteroid so we can deflect it out of the way. But you're right, if it's a rubble pile, then that does add an extra bit of complexity. And I think the key would be to do it as early on as possible so we can shift its trajectory enough that all the bits will miss the Earth.
And what have you learned so far with what you've got? What's been the sort of take home from the samples that have arrived back on Earth from Bennu?
Oh, well, we've learned so much about Bennu already, and honestly, there's more to come. So my colleagues and I are still working really hard on Bennu. But the project that I've been most closely working on at the moment is looking at salts in Bennu. So we found that there are salts like table salts, sodium chloride, also phosphates and carbonate, sodium carbonate in Bennu. And we think that these formed in a brine. So there was pods of actual water, salty water, underneath the surface of Bennu's parent body, which slowly evaporated away and left behind these salts. And this is really interesting because we think we see brines across the whole solar system. So there's a moon of Saturn called Enceladus, for example, that spews brines out, and we can see them on other asteroids like Ceres. So this might be a really widespread process that happens across our solar system that we're having a chance to actually look at in our labs today. And we think that these brines may also help catalyze organic reactions. So we might actually make important new organic reactions inside these brines. So our organics colleagues have been looking at this in Bennu, and they found nucleobases and they found amino acids and all of these molecules that are really familiar to us as being the building blocks of life.
I was waiting for you to say, watch this space. We made a
Yes.
programme last week about chiral chemistry and the
good.
handedness of molecules. And one aspect of that looked at astrobiology and the possibility that life out there uses mirror image chemistry.
Yeah.
Are you looking at chirality in these samples, and are you seeing any interesting trends there?
Yes. So again, I'm not on the organics team, I'm only on the mineralogy team, but my organics colleagues have been looking at this. And the thing that they found, which actually blew their minds because they weren't expecting it at all, is that Bennu seems to be racemic, which means that it has equal amounts of left-handed and right-handed versions of each of the amino acids and other organics. And that's different to what we've observed before in meteorites that do seem to have the same bias that life has. And what that slightly sadly means is that maybe our meteorites are contaminated by being on Earth and not being curated as beautifully as the Bennu asteroid is being curated. Ideally, would love to get more asteroidal material to try to test this. But yeah, it's really interesting to see that Maybe the organics in Bennu have both left and right-handed versions. So maybe life on Earth, when it started, it picked a team. It decided to go one way. And from then on, all the life on Earth became that way.
And we really will be watching this space because those discoveries haven't even been published yet. And I guarantee there's plenty more to come, I am sure. Thanks very much to Sarah Russell. This is The Naked Scientists with me, Chris Smith, and this week we are exploring the field of near-Earth objects, things that could slam into us from space, including why they matter and what we can do about them. There is the possibility that an asteroid called YR4 could be on an Earthbound course, with its arrival coinciding with Christmas 2032. Both NASA and the European Space Agency now say that is thankfully highly unlikely and it will safely pass our planet by. But can an impact be entirely ruled out? And how do we know what the odds are? Alan Fitzsimmons is a professor of astronomy. He's at Queen's University in Belfast and he's part of the Atlas project that first observed YR4.
YR4, we believe it's a small near-Earth asteroid, somewhere between 40 metres and 90 metres in diameter. That was first picked up by our telescopes, our survey telescopes, in December last year. And ever since January, when we realised that there was some possibility of it hitting us in a few years' time, it's been closely monitored.
How do you actually go looking for these things? Or do you just sort of chance observe them? Or is there actually an active process looking for things like this?
Well, at the moment, there are several NASA-funded sky surveys just looking for these near-Earth asteroids and the few near-Earth comets. And in fact, they're so successful, it's generally not realised that on average, about 7 or 8 new small asteroids are discovered that can pass near our planet every 24 hours. Now, the thing about an asteroid is that it doesn't emit its own light. It just reflects sunlight. And the bigger it is, the more sunlight it reflects. But from Earth, it still looks like a star because asteroids are so small. Even when they're close by, they appear just as a point source of light in the night sky. And so these survey telescopes that have been set up by NASA, but in fact, I must say that the European Space Agency is just starting to set up its own network of surveillance telescopes. Every night they sweep through the sky and they're simply looking for objects that weren't there before, first of all, but also that are moving against the background stars and galaxies, because indeed that's how the ancient Greek astronomers identified the planets. The planets move against the background fixed stars, and that's because they're orbiting the sun. Similarly, although much fainter, when we see these near-Earth asteroids passing our planets, they're also moving against the background stars and galaxies. And so that's how we first identify them.
And your asteroid, YR4, where is it right now?
It was detected, of course, when it was passing close to us, but it's now actually heading out towards Mars's orbit. It's actually more than halfway between the Earth and Mars in its own elliptical orbit about the sun, an orbit that it's had for decades, and it will have at least for the next 7 years. And so as it moves around the sun, it's been getting fainter and fainter, and that's why we've had to pull in more and more larger telescopes to track it and measure exactly where it is and plug those measurements into the orbit calculations to figure out where it's going in the future.
When policymakers, that kind of thing, are saying, well, you've spotted this, what do we need to do about it? How do you make those sorts of calculations to say, well, the odds are it will or it won't end up crossing the path of our planet? What the odds are that we're going to basically have a very, very close encounter with it?
Well, this is the problem we have of communicating risk, because when we measure the position of these asteroids in the sky and we fit an orbit around the sun to it and we calculate where that object is going in the future, everything has some amount of uncertainty to it. And so when we first detect an asteroid, we have only really a rough idea of its orbit about the sun. So we can say that we think this is the orbit that it's got around the sun at the moment, and we think it's going to go near our planet at some point in the future. But at that date in the future, we don't know exactly where it's going to be. Now, as we get more observations, we narrow down the possible orbits about the sun.
Is there
So
a sort of protocol for what you do if you see something? Is there like a giant red telephone to head office, and so you have to pick that up and make that metaphorical call to say, well, look, I've got something I'm really rather worried about.
Well, there is a protocol, and that's actually that was developed several years ago when we knew that eventually, at some point, we will find an object that is threatening, or even worse, is definitely going to hit us. So, first of all, the important thing to realize is that these calculations on the risk of an impact are done independently at least two sites, one run by NASA at the Jet Propulsion Laboratory in California, and one by the European Space Agency at the Near Earth Object Coordination Center in Italy. They are just taking the same data reported essentially by all astronomers around the world of all asteroids and updating the data every day and updating the orbits every day to figure out where these are going. Now, if one or both of these centers, as will happen with YR4, realize at some point, oh, the impact, the possibility of this asteroid is increasing, and it's started to look worrying, then of course you devote more resources to it.
It strikes me, is this a scientific opportunity? Because normally we have to deploy spacecraft to go and find these things, to go and visit them. As we heard with Bennu, the OSIRIS-REx mission had to go all the way to it, survey it, sample it, recover the specimens, bring those down to the Earth's surface. Very complicated, ultimately successful, but very expensive. If this thing is coming to us, that must be a huge scientific opportunity, if nothing else.
Oh, absolutely. And certainly in terms of science, the fact that these small asteroids pass close to our planet allows us to study them in detail, not only with our telescopes on Earth, but also with space missions, because these small asteroids are very difficult to study, even with the world's largest telescopes, when they're lying in the asteroid belt beyond the orbit of Mars. But interestingly, there's also a commercial opportunity here as well, because in recent years, in the last decade or so, there have been several startup companies based both here in Europe and also in the States, which have been looking at mining asteroids, because asteroids tend to be, or many of them tend to be metal rich, and there can be certain elements in there that are quite important and worth quite a lot. And it would be nice if both could piggyback off one another in the future.
I mean, it all sounds quite encouraging, what you're saying to me, both scientifically, but also in terms of us not being wiped out by this thing. But if it's not going to hit us, what is it going to hit?
Well, the good news is that the chance of an impact, at least in the year 2032, is now pretty much ruled out. But it's going to pass pretty close to the moon. Now, over the recent days, the chance of impact on the moon has hovered over 1 or 2%. If it could hit the moon, that would be a tremendous opportunity for astronomers and scientists on Earth, because it would cause no real ill effects on the moon apart from making a new crater, and it would have no effect on our planet, but would be able to observe the crater making process by a small asteroid in situ, and that would be a fantastic opportunity for science.
Alan Fitzsimmons, one of the team who discovered YR4, the 2032 Christmas present we really don't want coming down our chimney. Finally today, we're going to talk about what we can do if we do detect an incoming threat, and also whether the moon might play a role in studying and protecting us from asteroids and comets that come close to Earth, including possibly YR4. Here's the space scientist and author David Whitehouse.
There's only two things you can really do. You can either blow the thing up, or you can nudge it out of the way. If you could blow up an asteroid of the size we've been talking about into a million little pieces, that would actually be fine, because a much smaller piece would, if it did to strike us, would burn up in the atmosphere. If you split it into two, then that wouldn't help you all that much, because it would still be two very large chunks. So in order to blow something up, you've not only got to know what it's made of, but you also have got to put the explosion inside the asteroid. And unless you're a science fiction film director, that's a very tall order indeed. So what seems to be the best thing to do would be to actually put, say, a nuclear weapon on one side of the asteroid, so that when you blew it up, you were using the recoil to change its orbit, strategically placed at the right point on the asteroid, so that it didn't destroy too much of it, but most of it was actually pushing it away from its orbit, changing its velocity in space for perhaps only a few tens of meters per second, would be enough to wear it out completely from striking the Earth. This is all theoretical, except for the DART mission to the asteroid a few years ago, which actually gave us a great deal of important information and showed that impact and possibly explosion is a very good way to do this.
So, what opportunities does the moon afford us for informing ourselves about this then, and best ways about it, best practice?
There are certain orbits which, particularly close to the sun, which it's difficult to monitor, which you might get a better handle on from the moon. So it's not impossible that at some time in the future, when we have improved our planetary detection system around the Earth, to put an outpost on the moon to look at these particular orbits. As for experiments as to how to blow pieces of rock up, you could do that on the moon, but they say there will be international treaties which will object to this. It was suggested early on in the moon's exploration that people blow up nuclear weapons on the moon as a demonstration of political power, and that wasn't regarded as a good idea in the end. So, yes, the moon could make a contribution as a sentry, but all the experiments that you would need to do are probably best done on real objects so you can measure deflection and effect like we did in the DART mission.
The moon has been hit a lot, though, over its lifetime. If you go around the far side of the moon, for example, you can see it's an amazing landscape, all these impactors. Is there anything that what has already happened to the moon can teach us about why this happens, how it happens, and ways in which we might mitigate?
Well, the moon teaches us that we're very lucky to live at the time we do, because most of the impacts on the moon, as you say, it's a battered, violent, chaotic landscape. But most of those impacts happened a long time ago. If there was life on the Earth billions of years ago, then it wouldn't have lasted very long during some of the major bombardment instances, because everywhere was pummeled, sterilized by these impacts. So what you get from the moon is the history of the solar system. You get some information about what type of objects they are, about the reduced rate of impact that there is in our time in the solar system. You can have a rate of impact calendar from the moon, which shows that very few things happen at the moment. But statistically, it's not the small things that bother you. It's the abnormal outliers, the larger than usual objects, which are extremely rare and will probably not come along more than once every few decades or so. But from understanding the moon, you piece together a picture. But I think that most of the picture we need is going to come from the objects and spacecraft that have gone to asteroids and examined them.
What then, to your mind, are the experiments that should be done or are being done in order to really, I think, have a plan, a battle plan for when this threat does surface?
One thing that really impressed me over the last few weeks is how people took notice of this. Not just journalists and people writing about it with lurid headlines, but actually the space agencies. And particularly in America, the organizations which are, if you like, planetary protection oriented, they knew about this thing very early on. They had a very realistic understanding that the probability probably would go down, but they were actually quite prepared to actually get cracking on something if they lost this object into deep space before they had shown that it was not going to hit us. I was quite impressed by the behind the scenes discussion. We understand from the DART missions, we have the technology for an object of this size, because the asteroid that was struck during DART is larger than the one that threatened us, and we had a more of an effect on that at orbit around its parent asteroid than we anticipated. So the data is coming in, the experiment at DART was very good, and the organization seems to have worked this time. Now, everybody, of course, is very, very thankful the thing's going away, but had it not, then personally, I was quite impressed by the fact that people were ready to start acting.
Which is very encouraging. That was former BBC Science editor David Whitehouse there. In sum then, space scientists do have our backs on this one. There are missions prowling the skies looking for potential threats. Scientists have better insights now into the compositions of the possible impactors, and they're making intriguing discoveries in the process about early life processes on Earth. Meanwhile, experiments like the recent DART mission are beginning to test out ideas for how we can defend ourselves and deflect possible impactors if the worst should happen. But let's hope it never comes to that. Next time, back here on Earth, Will Tingle will be taking a look at genetic engineering and the technique termed CRISPR. It's won a Nobel Prize, but what exactly is it? Is it dangerous? And what will it deliver for us? Find out next time. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It is supported by Rolls-Royce, and it's also very much supported by you at home. Thank you so much to those of you who have given us donations, either in a one-off capacity, and also those of you who have a regular monthly or annual plan with us. We're really grateful. It makes a massive difference. And if you'd like to join the ranks of people helping us out in this way, you go to nakedscientist.com/donate. That's nakedscientist.com/donate. Thanks again. I'm Chris Smith. From all of us here at The Naked Scientist, thank you for listening, and until next time, goodbye.